Hello, Mr. Halpern. Welcome to my presentation on Kaya, Lily, me, or Reed, and I. We made this poster board right here, and this is my science presentation. So you can see at the top of our thing, it's separated into two things. It's separated to an atom and a periodic table. And I'm briefly going to talk about the periodic table. So it was founded by this version of the periodic table was created by I have a piece of paper right here just for notes. Was created by Dmitry Mendeleev. And the way it works is that, like for example, number 1 is hydrogen. That means that it has 1 proton, or its atomic number is 1, and it keeps going on like that. And it's separated into rows and columns, or in other words, a column is a group, and a row going this way is called a period. And there's going to be many different trends using those columns and periods going throughout this presentation today about electronegativity, ionization, and atomic radius. What was actually very interesting about this guy, Dmitry Mendeleev, when he was forming the periodic table, there were a couple of elements that were missing, and because of his format and the way he figured it out, he was able to establish certain characteristics of the elements that they were still missing before they even found them. And the periodic table is split up into 4 different sections. The S section, which is these first 2 columns. Then it's the F section, which is these things, but they go into these 2 rows. Then it's the D section, which is these 10 columns, and then it's the P section, which is those 6 columns. And at the end of the P sections is noble gases. The next main topic of our presentation is the atom, which is right here. So the atom in the center is the nucleus, which is made up of protons and neutrons. And then there's several outer shells depending on what period you're on. So there's one shell per period, and on the shells are electrons, which are negatively charged, and the nucleus are protons. And those 2 are attracted to each other, and that attraction will affect these trends, and they're actually kind of based off of that attraction, and atomic radius is the size from that. This is the amount of energy required to move those electrons, and this is the attraction, which I just referenced. So as you go down, each element has its own, it's called a valence electron, which is the outermost electron on the outermost shell. Now I'm going to go into detail about the 3 different trends our group learned about. So first of all is atomic radius, which is essentially the size of the atom, and it's measured based on the distance between the nucleus and the outermost shell. But another way it's often measured, because atoms are always moving, it's very hard to measure them. You can measure the distance between the nucleus of one atom to the nucleus of another atom divided by 2. Which is talked about there. And the trend that you see on the periodic table is that size decreases as protons and electrons are added. So in other words, as you go along a period, the size gets smaller, and as you go down a group, the size increases. And the reason for that is because as more electrons are added, that means that the pull as more electrons and protons are added, the pull becomes greater, and it kind of condenses the atom, making it smaller, which is exactly what atomic radius is. So this is electrons and protons being added, or in other words, the atom becoming smaller, and that's the trend going across a period. And the trend going across a group is once you get to the end of a period and the atom is at its most condensed version, once you open up a new electron ring, it uncondenses again. It kind of like separates again. That's how it was explained to me, and I think that's very helpful. And as you can see in this graph right here, or you might be struggling to see, there's a spike on all of the first elements in a period, and that's because that's where it's the least condensed based on the size. And then, sorry, my dogs are barking. But there are some anomalies in it, which I'll get into detail about now. So I have 2 little pictures pictures printed for you right here. There you go. Sorry, that might be hard to see. That's CR and that's MN. And that's an anomaly because you would think that as you go down, it gets smaller. And you can see them right here, CR and MN. You would think that MN would be smaller because it's closer and it has more protons and electrons and the pole is greater. But that's actually not true. And the reason for that is because I'll show you the two formations right here. You can see that in CR there's 1 electron in 4 orbitals and missing 1, and this one has 1 in each. And when there's 1 electron in each orbital, an atom is momentarily more stable than it normally would be. So for Mn, when it's more stable, that it decondenses a little bit, and it gets slightly larger. So it gets smaller, slightly larger, and then it continues to get. Sorry, my computer turned off. It should turn back on in a second, and then it continues to get smaller, and smaller. To talk about my analogy, I use my analogy as a tree, and that kind of relates to the way you're looking at it, because as you go down a tree, the stump becomes kind of larger, which is the same thing that happens as you go down a group, but as you go out the branches, it starts thick and becomes thinner, which is the same thing which happens at period, and thickness is the same, is in relation to atomic radius. The next topic I'll be covering is ionization. So with ionization, ionization is the amount of energy required to move electrons. So if for whatever reason you want to remove an electron from the atom, it's determined by ionization. The trend that you see in ionization is energy increases across a period. So the amount of energy required to remove it increases as you go this way, and it decreases down a group. So the amount of energy decreases going this way. And a way I like to think of it is like, if there was an arrow going like that, like pointing up to the right, that would kind of explain it, because the bottom left is the least energy and the bottom right is the most energy. And the reason it's more energy when the electrons are closer to the nucleus, for example, in fluorine, which is where there's the most electrons closest in the orbital closest to the nucleus, is because the charge is very, very strong, and it's very close to the nucleus, and it'd be very hard to remove an atom. But if you go all the way down here to Fr, the outermost electron is super far from the nucleus, and the pole is not as big, which I'll be talking about in electronegativity, that pole. And when the pole isn't as big, it becomes much easier to remove an electron. And then they were right here, it creates cations. Mr. Halpern taught us that it's like a positive ion, like cat paw. So it creates a cation when you move an electron from the atom. And then their analogy was like a parking lot, and the closer you are to the center of the parking lot, the harder it is for you to get out. Just like the closer an electron is to the nucleus, the harder it is for it to be pulled out. And then the further you are from the center, so like if you're on the edge of the parking lot, it's easy to get out. Just like how the further away an electron is from the nucleus, the easier it is to pull it out. Oh, I quickly wanted to talk about an anomaly in the trend. So I have a picture, sorry, going off camera. I have a picture right here of nitrogen and oxygen. So there's nitrogen and there's oxygen. And it's a similar thing to last time, where there's 1 orbital in each, or 1 electron in each orbital here. And in this one, there's 1 electron in each orbital and then 1 extra here. And as I mentioned before, 1 electron in each orbital is slightly more stable than 1 electron in each orbital with an extra electron in 1. So that means, based off of stability, if you were to look at the graph for, let's see if we can get it, ionization. So if you were to look at the graph for ionization, which is up here, you would see an anomaly in those 2 elements, which I just talked about, nitrogen and oxygen. And the amount of energy required to remove an oxygen atom, which is further away from the nucleus, is actually slightly less because this one's more stable. Because nitrogen's more stable because it has those singular electrons in each part. The next topic I'll be talking about is electronegativity. So electronegativity is the ability of an atom to hold electrons tightly. So Coulomb's law over here states that like charges repel each other and opposite charges attract. And as we know, protons and electrons are opposite charges. Protons are positive, electrons are negative. So protons innately want to attract to electrons, and electronegativity determines that ability. I'll first be talking about the trend. So as written here, the trend for electronegativity is actually the same as ionization. So in the same way, I like to visualize an arrow going up that way, and fluorine, which is the element on the top, this element on the top right, has a very high electronegativity because it's able to hold electrons very tightly, because it's very stable because it's super close to being a noble gas, and its outer ring is super close to the nucleus, meaning its pull is very strong, and this is essentially the pull. So the pull is strong because it's close to the nucleus, and it's very stable because it's close to the noble gases. And there's a picture I have here that I like to use for that, and you can see on the top right, fluorine is the darkest color, and like darkness represents electronegativity, and then you can predict it like this, like as you go across a period, the electronegativity becomes greater, and as you come down, the electronegativity becomes less. As you go down a group, the electronegativity becomes less. Electronegativity talks a lot about atom bonding. So when researching this, the first question I asked myself was, why do atoms bond? And atoms bond so that they can become more stable. So electronegativity often involves the process of atoms bonding to become more stable. And there's many different rules to this. And when you have a polar bond, that means that 2 of the electrons will be shared. When you have a non-polar bond, that means that the electrons will all be evenly split. And when you have an ionic bond, that means that one of the atoms will give the other atom 2 of its electrons. And then, as I was talking about, X is the difference of electronegativity between 2 atoms. And then, as I was just saying, electronegativity and ionization have many relations to each other, and there's many lines that connect them. Like, for example, this line showing that they have the same trend. So I'm going to give you guys 2 examples. The first one is going to be iron, which has an electronegativity of 1.83, and magnesium, which has an electronegativity of 1.31. So the difference in those 2 atoms is 0.52, meaning that it's above 0.5 and less than 2, so it's a polar bond. So that means that they're going to share 2 electrons. Those 2 atoms, iron and magnesium, will share 2 electrons. And then if you're looking at a bond between fluorine and cesium, which is a very major bond, fluorine being at the top right and cesium being closer to the bottom left, fluorine has a 3.98 electronegativity, while cesium has a 0.79 electronegativity, and the difference between their electronegativities is 3.9, meaning that it's ionic because X, which is the difference of their electronegativities, is greater than 2. And when the difference is greater than 2 and it's an ionic bond, that means that one of the atoms will give the other atom 2 of its electrons. So that's what happens when you combine fluorine and cesium. So I just want to reiterate this. When you're looking at the graphs of the atomic number based on these 3 concepts, there are going to be outliers, and there's a justification for every outlier, which I have been talking about. And the example I've been using is I'll pull it out for you guys. Cr and Mn. Cr is there. Cr has 4 orbitals with 1 electron, and Mn has 5 orbitals with 1 electron each. And 5 orbitals is more stable and more stability. For example, in a case of atomic radius, means that although the atoms are condensing, when it becomes more stable, it becomes slightly bigger. So 25 will be bigger than 24, even though the trend is that it. So I'll point to it again. Fe will be bigger than Mn, even though it gets bigger, or it gets smaller as you go this way, just because of that change in stability. And the same is true for ionization, which is the amount of energy required to remove electrons. Well, it's not the same. It's actually the opposite. Because which I'll get into detail in a second, but this directly correlates to the distance between the nucleus and the most outer electron, and it also correlates with electronegativity and stability. So if the stability of the atom is more stable at 25, then it will require more energy to take an electron from a more stable atom than it will from a less stable atom, which in this case is gonna be Cr. And then the same goes for electronegativity, which measures the attractions of electrons towards the atom's own nucleus. The attraction. So in any case where you're talking about electronegativity and ionization, the trend will be the same. And thinking about it, an arrow going up to the right is the trend, and then atomic radius, it's an arrow going down to the left. And what's interesting is in these graphs, you can actually see that trend. Looking at similarities in these graphs, these ones start low at the beginning of each period. They start at the bottom and they go up. And electronegativity atomic radius starts at the top at the beginning of a period and slowly goes down. Again, I just wanted to reiterate our connection, the main connection to Coulomb's law, which was opposite charges want to attract, opposite charges being the protons and the electrons. If they want to attract, that's the same thing as electronegativity. So electronegativity is very similar to Coulomb's law, which is it's measuring the attraction of those opposite charges, which are the atoms that want to combine. The next thing I wanted to talk about, one of the honors topics, is shielding. So this is a graph that really helped me understand how shielding works. So it's kind of like, let me see if I can figure this out. If you can see right there, that electron on the s orbital is getting in the way of that electron on the p orbital, and that's what shielding is, and that interferes with the bond between the nucleus and that electron. An analogy of a way I like to think about it is like, if you were to put a piece of paper between two magnets, the magnetic pole would become slightly worse, and that's what happens in the shielding process. And then I had a picture here for you. I have a picture here that demonstrates that. So let's see. You can see rubidium here. So it obviously has 5 different shells, and the outermost shell, which represents the fifth period here, is here rubidium. The outermost shell is going to be shielded by all the electrons from the shells before it. So you can see in this graph that this top electron is being blocked by 4 more electrons, and that's what the process of shielding is. It's that blockage. The next honors topic I wanted to talk about is ground state versus excited state. So the ground state is an atom when it's in a standard form. So when the electrons are all in the right shells and there's nothing out of order. And then an atom can become excited. One example is when it's when it's shown heat. And when it's shown heat, the electrons can move from one shell to another, and they can move out of their orbitals to different orbitals. An example of this is neon, whose orbital's configuration is 2,8, can become 2,6,2, which means 2 of those electrons moved to a new ring. And then you can determine excited state based on colors. So I have an example right here. These are 4 different fires. This is a typical methane fire, and when you add different elements to it, those elements become excited and they change color. So when you add iron to it, it becomes like an orangey thing. When you add aluminum, it becomes more whitey, and when you add boron, it becomes it gets like a greenish characteristic. And then rules of exciting. There's a couple rules. So any number of electrons can excite. So if all the electrons can go to the wrong place, but it's typically just as much as two electrons get excited. The next thing is an electron cannot move to a shell that's already full. So in the example we just talked about, which was 2 and then it was 8, it can't go 1, 9 because 8 is already full. The second shell is already full. You can't add another one. The next rule is you can add electrons to a new shell, which is going to affect ionization, which I'll talk about in a second. And then the third rule is eventually an excited state will always return to an excited state will always return to a ground state. So I'm going to talk for you on this is one of my honors concepts. How does ground state and excited state affect ionization energy? So ionization energy, as we know, is based off the distance from the nucleus to the outermost electron. And if, for example, an electron moves to a new shell and creates a new shell, that means that the new outermost electron, let's just say this example is 2, 6. So there's 2 electrons in the first shell, 6 in the next shell. If you were to change it to 2, 4, 2, then it'd be 2, 4, 2. The distance is becoming greater, which means the amount of energy or the ionization energy to remove that for the new furthest electron decreases. That's how ionization energy is affected in this concept. The next thing I will talk about is for my honors, for the honors students, we were given two elements in a period and 2 elements in a group, and we had to talk about them with the trends. So in a period, I was giving Na and Mg, and I'll talk about that and how it relates to the trends for each of these 3. And for a group, I was given F and Cl, and I'll do the same for all 3. So let me start with atomic radius for both. So in atomic radius, which is Na and Mg, we know that as you go across a period, the atomic the atom condenses because the attraction becomes greater because of more protons and electrons, and therefore the atomic radius becomes smaller. So the atomic radius of Mg is going to be less of that of Na. And then let's talk about it for a group. So we have F and Cl, fluorine and chlorine, and as you know, as you go down a group, the atomic radius becomes greater because you're increasing the amount of shells, and therefore it increases the circumference of the atom. So chlorine is going to have a larger atomic radius than fluorine. Now let's do the same thing for the next 2. No biggie. So for ionization, we know that the energy increases across a period. So Mg, magnesium, is going to have a larger ionization energy than sodium. And then the same goes, and then for a period, energy decreases down a group. So chlorine is going to have less ionization energy than fluorine. And I'll just do a quick explanation for that. So for magnesium, as you add more elements and it becomes more stable, the energy, when it's more stable, the energy required to move an electron becomes greater. So since magnesium is closer to reaching the end of its period, the amount of energy required to move its electrons is going to become greater. And then it's the opposite for a, sorry, that just turned off. It's the opposite for a group, because, yeah, it's the opposite. As we know, it's the opposite for a group. So the amount of energy required to move, remove chlorine is going to be less of that for fluorine. And the reason for that is because fluorine is super stable. It's super close to being at the end, and it's also super high up, and it's very close to the nucleus, which means the pull is super strong. So removing fluorine is going to be super hard. but chlorine is slightly further, meaning that it's going to be easier to remove it. And now we just have to do that for electronegativity. So in an electronegativity period, for Na and Mg, it's the same trend here. So as Reed wrote, did he write it? No, he didn't, but it's the same trend. Energy increases. Oh, actually, they made a connection there, which is very helpful for me. Energy increases across a period. So the attraction of magnesium towards the center is greater than that of sodium towards the center. And then for a group, the attraction of fluorine towards the center is greater than the attraction of chlorine. And we know because fluorine is in a closer orbital, meaning that it's closer to the nucleus, and the charge is stronger there, and chlorine is further from the nucleus and the charge is weaker. And the explanation for Na and Mg, as we know, as you increase the amount of protons and electrons, it gets more and more condensed because it's becoming more and more stable, meaning that it increases, so the amount of energy required to remove magnesium, which is more stable than sodium, is going to be greater. And it goes the same for the pull towards the nucleus. Yeah, and then I have not touched on Reed's his analogy yet. So Reed's analogy relates to the 3 different types of bond, and he talked about it as if it was like tug of war, and it's because, like, let me get my picture out again. The difference, like, the higher the electronegativity of one. So if fluorine is having a tug of war with cesium, fluorine's going to demolish cesium, and it's going to end up giving it 2 of its electrons. And if it's a very, very, very tight 2 of 4, and the electronegativity between the difference of electronegativity between the 2 is less than 0.5, then they're just going to end up sharing their electrons. Yeah, I think I got it. Thank you.